Hello again, and welcome to another live stream of Chemistry 223. This is brought to you by the Portland State University Learning Center and your teachers for Chemistry 223. Today we were going to talk about strong acid and strong base titration, as well as weak acid and strong base titrations as well. First, I must apologize. We missed last week because I was busy. On Friday, my youngest son, Benjamin, was born. Give you a picture. There's a picture of him there. He's doing well. He came out at 9 pounds and 5 ounces, but I was unable to show up last week to help you guys with your midterm review. For that, I apologize. But this week, we're back, and we're going to talk about titrations and other things like that. Thank you very much for the congratulations. I appreciate it. Hopefully your midterm went well if you had one, and we'll go forward and we're going to talk about titrations today. Let me go back to this. First, I also wanted to post a few links in our chat as usual. First link is a link to the Portland State's Learning Center webpage. There's a lot of great resources there. They try to update it periodically, so check back every now and then to see if we offer new things. If you follow them on Facebook or Instagram, you can also get updated when they add new things. So there's the Facebook link and the Instagram link here. Also, if you ever have any questions, feel free to make an appointment through Penji with any of our wonderful tutors for any of the subjects that we do. We have tutors there for sciences, math, languages, and a variety of other things. So definitely check it out for any of your classes that are there. We also have academic coaches that just kind of work you through kind of navigating the whole university environment. So if you have a question on where I should go next or what I should be doing, definitely try to check in with those academic coaches. You can find those links through the Learning Center's website as well. So let's get started here. We're going to talk about titrations. So in the past few weeks, we talked a lot about how to calculate pH for strong acids or pHs for weak acids at equilibrium, weak bases at equilibrium states. And you guys went into buffer systems, which is something I was going to cover last week, but we missed, using the Henderson-Hasselbalch Equation. I'm going to do a quick review of all of these things because we need to use all of this when we start talking about titrations. So the first thing we learned was how to calculate the pH using the concentration of hydronium ions. I usually write this as just hydrogen ions, and hydroxide, the concentration of hydroxide. And we do that using just that basic logarithmic equation that we have, where the pH is equal to negative log of the concentration of H+. Similarly, we can find the pOH, which is equal to the negative log of the concentration of OH-. You guys should be fairly familiar with this at this point. If you're still struggling with this, definitely make an appointment with the tutoring, and we'll make sure you can understand everything properly. But this is the basic idea on calculating the pH if you have that concentration of hydronium or hydrogen ions. You can always find the pH if you know the pOH, because that's going to be equal to 14 minus the pOH. And this works for strong acid. So if you have any strong acid or any volume of strong acid, and you can always find out the concentration of that and then use it to find the pH. But that's because strong acids and strong bases, they fully dissociate. Which means that their for a strong acid, the conjugate base is very stable as a base. So it's not really it's a very weak base, essentially, for the very strong acids. And subsequently, the very strong bases have a very weak conjugate acid, or a very stable conjugate acid. So they're not trying to pull up any, they're not trying to lose their protons at that point. So that's how we calculate them for any of the strong acids or strong bases. But when we have weak acids or weak bases, things get a little bit more tricky, and that's where we get this idea of Ka values and Kb values. So pH for a weak acid and bases using Ka or Kb. So the Ka value, we know, is just that concentration of the products, or say the products divided by the reactants. So if we take any weak acid, which I'm designated by HA in this case, we can find its equilibrium constant by taking the concentration at equilibrium of hydronium and the concentration of the conjugate base that's created, and divide that by the concentration of the acid that's in there. And if we have some value, when we do our ICE tables to figure this out, we have that value x, which is really the change, whether it's going to be, if we're decreasing the amount of acid that's in there, it's going to be a negative value. But if this value is much less than the initial concentration, we can say, and we can solve for it using this guy. It's just a rearrangement of our Ka expression on the left. Oops, drew that wrong. Boom. Is equal then to the square root of Ka times HA. So that's the Ka value times the concentration of the acid. And to find the Ka values of these things, we can usually look them up in tables, because a lot of people have experimentally figured these things out for us in the past. We can similarly find, or I guess otherwise, if this isn't true, we can use the wonderful quadratic formula. And this quadratic formula tells us that concentration of hydrogen ions using this negative Ka plus the square root of Ka squared plus 4 Ka times the concentration of the acid. That whole thing is to be divided by 2. So this value, this quadratic will always work. It'll always give you the right answer, but sometimes it's more work than you need to do. If you can approximate it using this, go ahead. Again, anytime you have it where that change is going to be insignificant, because we always end up having that change, we're subtracting that x from our initial concentration. If our initial concentration is really big and our x is really small, it's just lost in sig figs. So we don't have to worry about it. We can do the same idea for Kb. Okay. And this is just kind of writing that same scenario out for Kb, where I have the concentration of hydroxide times the concentration of acid divided by the concentration of the base at equilibrium. And the same goes for this, where if that x value, that change, is much, much less than, in this case, the concentration of the base at equilibrium, we can simplify our OH equation and find the concentration of hydroxide is equal then to Kb times the concentration of our base, A minus. Otherwise, we have to use the wonderful quadratic in the base form, which is the same idea as above, where it's negative Kb now, plus the square root Kb squared plus 4 Kb times the concentration of the base at equilibrium divided by 2. So those are just kind of worked out. I've already done the ICE table in a generic form, and I just got this nice quadratic equation I can plug in. So if we find the Ka or Kb values, depending on which version we're looking at, we can plug those in with the concentrations of the acids or base subsequent or respectively to find the hydronium concentration or the hydroxide concentration, which if we plug these values back into our pH and pOH up here, we can solve for pH. So if we have hydronium from that, we can solve for the pH. And for a weak acid at equilibrium, we'd find those here. For a weak base, we'd find the PO or the OH values, and we could plug it in, find that POH, and then find our pH this way. So we'd find that situation for titrations usually at the equivalence point or at the beginning of the titration before we've added any of the base in for this regard. But in between those points, we end up with a buffer. And we kind of missed buffers last week. Again, I apologize, but a buffer is when we have a weak acid in solution with its conjugate base. And this works for weak buffer, or say weak bases and weak acids. And we use an equation called the Henderson-Hasselbalch Equation, which is the pH is going to be equal to the pKa. Now the pKa is the same idea as what we had up here. I'll write it here. pKa is equal to the negative log of the Ka value. Right? And we can also, if we needed to, find the pKb. This is found less often, but it's the same idea. You can take the p of anything, which is really just the negative log of, shouldn't be a concentration, I guess, just Kb. Yoink. Oops, big eraser, small eraser. So that's how we find the pKa, is taking the Ka value and using that negative log of the Ka value to find the pKa. But the pH here is equal to the pKa plus the logarithm of the ratio behind the concentration of the base over the concentration of the acid. And these are concentrations at equilibrium. So at equilibrium, we can find the concentration of the base and the concentration of the acid, and we plug that into that logarithm form. And we're basically going to be adding that to the pKa value. And this is called the Henderson-Hasselbalch. You've probably heard about it. And we're going to talk a little bit more about how all of these different types of equations work during the titration process and when to use which one as we go forward for our strong acid, strong base titrations, as well as our weak acid, strong base titrations. Any questions on what I've talked about so far in any of these equations? We're going to dig deeper into the Henderson-Hasselbalch equation when we get to the weak acids. Okay, if there's no questions, I'm going to keep moving on. And we're going to talk about then the strong acids. Let's go here. If you have a question, just feel free to chime in the chat, and I will try and answer it as best I can. So for a strong acid being titrated with a strong base, this means you have a beaker, and inside the beaker is a strong acid. It could be HCl, hydrochloric acid, or any of the other strong acids. There's 6 of them. And then all of these fully dissociate in water. And before you add any base in there, the pH of that solution is going to be equal to the concentration of the acid that you put in there. We can write out the basic formula here. So if I had HCl, which was aqueous, and I add to that then say NaOH, okay, some solution of NaOH I add into it, this is going to produce when the hydronium ions is going to produce hydronium and hydroxide, which are going to balance each other out, or say H plus and an OH minus, which end up just producing H2O as a liquid, plus you end up with the chloride minus aqueous and the Na plus aqueous. Now these two are essentially incredibly stable, being floating around in water, so they don't react with anything, which is why hydrochloric acid and sodium hydroxide are strong acids and strong bases. And this just leaves us with water at that case. So if we have any acid, if we add the equivalent moles of hydroxide ions to it, we end up with a neutral water. So the equivalence point, which is where the moles of acid is going to equal the moles of base, is always going to be at pH of 7 for a strong acid, strong base titration. For a weak acid titration, it's going to be a little bit different. It's going to be higher in that case. And we'll go over that in a little bit. But we can see that the concentration here of, I'll say, H plus is going to be equal to, I'm going to call it the moles of H plus. Put a little 0 down there for the initial amount of moles of H plus we have in our initial solution, subtracted from the moles of OH minus added. And then we need to divide that by the volume of our strong acid, the initial volume we had plus the volume of the strong base, the amount of water we added to that, because the concentration of hydronium is always going to be the number of moles of hydronium ions divided by the total volume of the solution. And as we titrate, we're basically slowly adding more and more volume to the solution. And that volume is incredibly basic. So that's why we're adding the two volumes together at the bottom, because at any point along that, our volume is going to be greater than what we started with. So even if we just titrated with neutral water, the hydronium ions would stay the same, but the volume is going to increase, which is going to reduce our concentration. So as I mentioned earlier, the equivalence point. If I could spell, that would be wonderful. The equivalence point is when we have the moles of our hydroxide or our hydrogen ions. The initial value is going to, or the initial hydrogen ions are equal to the moles of the hydroxide ions that we added. Excuse me. So that means that for every hydrogen ion that we had in the solution floating around in there, we've added an extra hydroxide to counter that. Those bond together, and this just produces a bunch of water, a bunch of neutral, this is going to be liquid water. So at that equivalence point, we have a pH equal to 7. And that's going to be true for any strong acid, strong base titration. Whether you start with an acid and you're titrating in a base, or you start with a strong base and you titrate in an acid. As long as both of those are strong, we're always going to have that equivalence point at 7. I can show, I have a graph here of a titration. In this one, we started out with a very acidic, let's move to my pointer. We started out with a very acidic species here, and as we titrated in, we're titrating in sodium hydroxide. Okay, it starts to go up. It goes up very slightly at first, because every time it adds that hydroxide, it's basically reducing the hydrogen ions in there, reducing the amount of hydronium, but it's also increasing the volume. So as it goes up here, and then it reaches this equivalence point. At that equivalence point, we are reaching the point where the moles of hydrogen ions initially are equal to the moles of hydroxide ions. So then the pH shoots up, and it centers right around that 7 point here. And if we continue to add more and more sodium hydroxide, we see this is going to spike. So even just a little bit more, we get a much higher pH, which means it's a much more basic thing, because now we're adding a strong base to a neutral. Anything after this equivalence point, we're just basically adding that strong base to a neutral. So if you were to calculate the pH here, over here, you'd be doing what I said back here, where I'm taking the initial hydrogen ions, and I'm subtracting the moles of how much hydroxide we added divided by the total volume. That's for this point over here. At equivalence, it's always going to be 7. Anything up here past this equilibrium point, we can treat that as just a strong base. So however much hydroxide moles we've added total minus the initial. So up here we can say the mole of OH minus the initial moles of H plus. That's the initial. Let me move that off to the side so it's a little easier to read. So anytime where it's a strong base, you just have to subtract out, because at first, over in this area, all the hydroxide you were adding was turning into water until it used up all the acid that was in there. After the equivalence point, the hydroxide is just floating around in there freely. So it's increasing the base level dramatically at first, and then it kind of levels off into this really high base. It eventually just keeps tapering up at a very slow rate as you add more sodium hydroxide in there. And make sure we're always dividing by our total volume. Because that total volume, we're increasing the volume as we add more hydroxide. So as you increase that volume, you have to account for that extra volume that you add, which is the initial volume plus whatever you've titrated into it. Any questions on kind of strong acid, strong base titrations? I know I kind of rambled through a lot of that. All right, if not, I'm going to move on to, I might mention also that this is when we started with a strong acid and we titrated in a base. If you were to start with a strong base and titrate in an acid, a strong acid for that matter, it would look very similar. This is our pH scale. This is the volume of strong acid that we're putting in. The main difference is it would be kind of reversed, like that. Because we'd start off at a very high pH because we have a strong base in there. And then as we titrated more acid, it would go down until we hit that equilibrium point. Okay, so again, this is still going to be pH of 7. But then we're going to treat this area down here as just a strong acid. Any acid we had after that is the concentration, or has the number of moles of acid that we throw in there. And we have to account for the total volume. In the same way we had here, the graphs look the same, it's just we flip it, because now we're starting out at a high pH and we're titrating down to a low pH. So let's talk more about weak acids and bases, or weak acid titrations. And we're titrating this with a strong base. Usually you titrate with a strong base that you know the molarity of, and you use it to find kind of the molarity of the weak base, or the basically the concentration of the weak bases, or the weak acid in this case, is what you would be trying to find. So for this, the chemical equation, we start out with some weak acid, and say it's aqueous, and we're going to add to that some sodium hydroxide. It's also aqueous. This is going to be more of an equilibrium. This is going to be in equilibrium with the conjugate base plus water. Plus, we're going to have a bunch of sodium ions floating around when we're all done. Because sodium's very happy just floating in water. It stays fully dissociated. So this is really a spectator, where this is our acid. It's a weak one. So we get a conjugate base. And then we have water, which is kind of the product of that acid-base reaction. It's always going to produce some type of water and a conjugate base. So for weak acids, we can say that each mole of OH minus that you add produces 1 mole of the conjugate base. So what's happening in here is we have this weak acid that's at equilibrium. It's happy. It's got some conjugate base in there as well, but it's got this acid in there, and we have this equilibrium state for that weak acid. When we add hydroxide to the reaction, some of the acid is like, hey, I'd rather bond to hydroxide. Hydroxide's a stronger base than my conjugate is. So we end up losing some of the weak acid to that hydroxide, and that produces more conjugate base. So if we were looking at the concentration of our weak acid, as we put in, for every mole of hydroxide we put in there, we lose 1 mole of our strong acid to it. We can also say that since the titrated solution contains both a weak acid and the conjugate base, it forms a buffer. So anytime we have a weak acid with its conjugate base, we have this buffer situation, a buffer system. So to calculate the pH of that buffer system, we can use the Henderson-Hasselbalch Equation, which is I'll write out. So the Henderson-Hasselbalch equation, I wrote it before, I'm going to rewrite it again. It's equal to the pKa plus the log of, it's always going to be the concentration of the base divided by concentration of the acid. You can also think of this as the moles of the base over the moles of the acid. Because in this situation, in all these situations, they're going to have the same volume. They're in the same jar, so they're going to have equal volume. And since concentration is just moles divided by volume, you have moles over volume all divided by moles over volume. So the volumes will end up canceling each other out. And we can see, based on this equation, a little bit more space, that as the titration progresses, the concentration of the base and the acid are going to change. So as we're adding in more base to it, we're losing our acid. So our acid is actually going to be going down, where our base is going to be going up. So this ratio in here is going to change, and that's going to affect the pH. And we can kind of see the different stages during that buffer system of how it affects the pH. I'm going to talk about kind of three of the main ones here. So initially, we haven't added anything into it, so it's kind of at this equilibrium state for the acid anyways. But once we start adding in that sodium hydroxide, we get a few different states that's going to happen in that buffer system. So if the moles of hydroxide that are added is less than half of the moles of your acid initially. So these are all the initial concentrations of them. So if you add so many moles of sodium hydroxide to it, and that's less than half of the moles of the weak acid that you started with, you get this in a situation where this ratio of the concentration of the base over the concentration of the acid is going to be less than 1. And that's going to be less than 1 because you haven't, this number on the bottom is going to be bigger than the number on the top. So we end up with this fraction where the numerator is smaller than the denominator, so we have a value that's less than 1. And with this, when we plug it into this Henderson-Hasselbalch equation up here, this log term, I'm going to say the log of that ratio, A minus over HA, is going to be less than 0. It's going to be negative. So then we can see, just plugging that value, if that log term is less, the pH, or less than 0, the pH is going to be less. That's a bad less than sign. Less than the pKa. If we had exactly 1/2, so that brings us to our second one, which is exactly 1/2. If the moles of OH minus that we add are equal to 1/2 of the moles of the initial concentration of our acid. So that means that at this point, half of our initial concentration has turned into its conjugate base. So we have an equal amount of those two. That tells us that our ratio of this guy, the concentration of the base over the concentration of the acid, is equal to 1. Now, when you have a logarithm, this same expression, log of 1, well, that's equal to 0. So if you were to graph your term, log of x, you would see at x equals 1, it's crossing that x-axis. So the log of 1 is going to be equal to 0. So that means that at this point, we call it the half equivalence point. This is half equivalence point. My app crashed. There it is, it's back. The pH is going to be equal to the pKa at the half equivalence point. That's just because the second term is equal to 0, so this term is going to be equal to 0 in that situation. So we just are left with the pKa. The third situation is when the moles of OH minus added is going to be greater than that 1/2 of the initial concentration, or the initial moles of HA. I say moles because you can use that concentration to find the moles, and it's the number of moles that's really important in that situation. So this tells us then this ratio of the concentration of the base over the concentration of the acid is going to be now greater than 1, which means that our log term is going to be some positive value, for a log divided by HA is greater than 0. Squeeze it in there. And that tells us then our pH is going to be greater than the pKa. And this makes sense because as we're adding base into our weak acid, our pH is rising. It starts off up here being less than the pKa value. As it passes this half equivalence point, it becomes equal to the pKa value. And then as it moves past that, the pH is growing. It's getting higher than the pKa value. And so we can use the Henderson-Hasselbalch equation to find the pH during this initial setup. And this is going to be true up until just before the equivalence point, basically at the equivalence point. At the equivalence point, you have added enough hydroxide ions to make all of the initial acid ions kind of turn into their hydroxide. But you do have a slight equilibrium still there. After that point, or at the equivalence point, we can say then, I'll say 4. So at the equivalence point, at that point, the Henderson-Hasselbalch equation doesn't work anymore, and that's when we use our quadratic formula. But you want to make sure for this one we use the quadratic formula to find the OH minus. So the one for the base, which is concentration of OH minus is equal to the negative Kb plus the square root of Kb squared plus 4 Kb times the concentration of that base divided by 2. And that concentration of the base, the volume of the titrant, that's a good question. So the volume of the titrant, so you should be able, when you're titrating, let me go back to here, you have an initial beaker that has your acid in this case in it, right? And you have that known volume. And you have this long titration vial, and it starts off with 0 up here because you've added 0 to it. As you add more, you can measure the volume of what you're adding. So this would be just some volume. So once you've, if you're monitoring the pH as you titrate in the base, at certain points when you hit the pKa value or you hit that at that half equivalence or the full equivalence, you can stop and you can measure the volume that you have in there. And knowing the concentration of the base, so we know this NaOH is at a certain concentration. This is a known concentration of the base. We can determine the moles of that base. And based on that, we can determine the moles of the acid that was initially in here. If we go all the way to the equivalence point, at that equivalence point, the amount of moles of base we added should be equal to the moles of weak acid that was in there originally. Does that answer your question? So for the strong acid, strong base, the volume was really important because we were using this type of equation to determine the moles, and then we had to divide by the volume. For the buffer situations, since all of this is based off of the ratio here, and again, I can write that ratio as the moles of the base divided by the moles of the acid instead. Cool. So the same idea here. We don't really need to know the volume of that as long as we have the Ka, and this concentration here kind of tells us that concentration. So we do need to kind of know the volume, but we can take the volume by the initial plus what we added to find that as well. So anything after that equivalence point, we can say the buffer is basically destroyed, and now we're just adding in a strong base to that. And we can see that here's a kind of a titration graph of a weak acid. So anything here, if this is our equivalence point, anything after that point, it basically, all the volume we add, a small volume of it shoots that pH up. So it gets really basic really quickly and then starts to level off. We can treat all of this as just basically the excess strong base that we're adding. So if we added, X amount of base to it at this point, we can, everything here we can say is the total moles we've added from the beginning minus X, whatever this was to get us to this point here. So any excess that we add, we can then just calculate that based off the moles of the base divided by the total volume. And we can find that total volume by taking our initial volume again, and then whatever the titrated volume would be. So at 40 milliliters here, which we'd have here, say we started out with 25 milliliters of our acid, we'd be at then 65 milliliters total. And then we just have to determine the excess moles of base that we've added from this point to this point. So that's going to be this many milliliters, and assuming we had, 0.5 molar, we could easily just multiply that 0.5 molar by the difference in volume here to find out that moles. So on this graph, I also wanted to talk about when to use each of those types of equations. Initially, before you add anything in here, we have this little region down here. When there's just a little bit of titrant or none at all, like right at the beginning, we can treat that just as the weak acid. Let me write that thicker. So just that, and you can see it kind of starts to level off, and then it looks a little bit more like our strong acid, strong base. And in this region here, okay, up until probably about where it's going to get into that tall part, we can call that our buffer. It acts kind of weird in this area and in this area. All the equations don't work. You lose some accuracy at that point, and there's some better buffer equations you can use, but I think they deal with that in a further class. But here we just use that Henderson-Hasselbalch equation for that buffer. So anything within that region is going to fall in there. And our half equivalence point is about halfway through that buffer, where the pH is equal to the pKa. And then we go up and we get to this point. Here we can say anywhere in this region, basically, we are at the equivalence point. Let's just say equivalence. So in that region, and notice in this dimension, it's a very, very small region, that X. Okay, it basically shoots up really high in that region. It gets But anywhere within that little small region there is our equivalence point. At that point, you would want to use your OH minus quadratic. And that'll tell you the concentration of the base. And from that, you can find the POH, subtract that from 14, and get the pH. Or you can use the Kw value, because we know that Kw is going to equal to the concentration of hydroxide times the concentration of hydronium. So if you take Kw and divide by your concentration of hydroxide, you get the concentration of hydronium. Take the negative log of that concentration, and you should be able to find the pH from there. So there's lots of ways to go around it. Remember, I had that pH cube in past ones. You can follow it from, around the cube on the right or around the cube on the left. You get to the same place either way. After the equivalence point, just as it starts to go here, in this whole region here, we just treat this as a strong base. So it's any excess moles of base that you add to that divided by the total volume of the solution at that point. And you can differentiate when you see these titration curves. If you look for like the little bumps like you see down here, you can see, oh, that must be a weak acid being titrated with a strong base. If you saw this whole thing flipped around and it was coming down, kind of like I drew for this one, this was a strong. But we could do something similar. See if I can draw this proper, where it curves up and then it levels off a little bit and then goes down. This would look a little bit more like a strong base being titrated, or a weak base being titrated with a strong acid. It's basically, if I drew it right, it's supposed to be just the flip of this one here. Any questions on the weak acid or the weak acid, weak base titrations, anything with the buffers, the Henderson-Hasselbalch equations that I can go into before I start diving into a problem? All right, let's try a problem here. I'm going to go for this one because we're got about 10 minutes left, so I think we can get through most of this. So this is a titration of a weak acid with a strong base. And we want to consider the titration of 25 milliliters of 0.1 molar of this compound here. This is acetic acid, I believe. It's CH3 COOH. It's a carboxylic acid with a methyl group on there. And we are titrating that with 0.1 molar of NaOH. So this is a weak acid. And this is a strong base. And they tell us the concentrations of both of those. And they have a volume, or initial volume, of our weak acid. They give us the equation here. This is the balanced chemical equation where the acetic acid, when you add hydroxide to it, becomes this acetate here, where it's lost its hydrogen on there, and we get H2O water produced from that. I could draw this out for you real quick. We've got carbons with 3 hydrogens on there. Then we have what's called a carbonyl, where it's a carbon double bonded to that oxygen, and then another oxygen here. In this acetate form, this oxygen's negative. Zoom in a little bit there. That oxygen's negative there, and it actually allows a resonance to form between these, where that double bond will kind of flip back and forth, resonating between those, allowing those 2 oxygens to share that charge. So if we were to do a formal charge on this, we would see that the formal charge would actually be lower, be about half, because it's -1 divided by the 2 different possible resonance structures. So that's that acetate ion there. And that happens when the acid part of it is just when this has its hydrogen on it. And then you have that carboxylic acid. So that's just to give you an understanding of what's chemically happening to that. But we want to calculate the titration solution after the additioning of the following volumes of NaOH titrant. So we have 4 different volumes, A, B, C, and D. So let's start with A. With A, we have a weak acid of this acetate, 0.1 molar, and it's in 25 milliliters of water. We have added 0 titrant to it. Which equation do you think we want to use for this? Any thoughts? If you want, I can flip back to here. As I didn't say it here, I probably should have. I said it here. When it's a weak acid, we want to use the quadratic equation for a weak acid. Similar, just the same idea when we're at an equivalence point, we want to use the quadratic equation for the weak base. Because at that point, you have a weak base in there, essentially. Oops, wrong one. This one. So here, we want to use, I'm going to write it out, negative Ka plus the square root Ka squared plus 4 times Ka times the concentration of the acid, all divided by 2. That's our, this is going to equal then the concentration of H+. And using that, we can then take the negative log of that concentration, which will tell us the pH. I'm running out of time here, so I'm not going to go through all of the number crunching for that, just because I want to make sure we talk about specifically how to find the other ones. For part B, we're adding 25 milliliters of the sodium hydroxide in there. Again, the sodium hydroxide is 0.1 molar, and our initial acid, acetate acid, was also 0.1 molar. If we're adding 25 milliliters of there and they're the same concentration, there's a special point that this is called. What is that point? So we've had equal volume of equal concentrations. The equivalence point. Perfect. So this is at equivalence point. So which equation should we use to find out the pH at that point? This is a weak acid being titrated with a strong base. Yeah, the quadratic again, but in this case, we want to use the quadratic equation for this hydroxide, or the base form of it, which is the same thing, but now it's negative Kb. Exactly. And we're looking at Kb squared plus 4 Kb, excuse me, times now the concentration of that conjugate base, A minus, in there, all divided by 2. And then from there, you can take the Kw divided by that concentration, which is going to equal your Ka, or which will equal your concentration of hydronium. And then take your negative log of your hydronium to find your pH. So it's the same idea. The only difference in these equations is we use Kb instead of Ka, and we're taking the concentration of that acid, or sorry, concentration of the conjugate base of our acid. So those are the only two things that really change. There's a derivation for it, I think, in the textbook, and you can definitely find it online if you do a search for it. It's really just all derived off of that Ka and Kb equivalence formulas. And we're just rearranging things around, and we're putting it into a quadratic form. And then you have your negative B, so this is going to end up being B, and C ends up being the concentration there, or these two for AC. Yeah, these two, I think. So what about C? What's happening for C? We have 12.5 milliliters in there. We're adding 12.5 milliliters of sodium hydroxide into 25 milliliters of our weak acid, and they have the same concentration. Which equation do we think we should use? Different options could be the quadratic for hydroxide, the quadratic for hydronium, just the basic pH formula where pH is equal to the negative log, the Henderson-Hasselbalch equation, or some derivative of any of those. Any thoughts? Yes, the Henderson-Hasselbalch. Because we're less than the equivalence, but we've added something in there, the Henderson-Hasselbalch equation is the right one to do. If you do that, you can go through all the math, and you'll realize that at this volume, which is half of our initial volume, especially since we had the same concentration, when we do this negative log of concentration of A minus over the concentration of HA, we're going to see that's equal to 0. So when we get that, this pH is equal to the pKa only, because this all cancels out. We call that the half equivalence point. So we've added half as many moles of hydroxide ions in there than the initial weak acid that we had. So we're at that half equivalence, and we're right at that pKa value. And to find that pKa, you can take the Ka value, which we can look up actually. So in the back of your textbook, pulled it up on the internet here, it lists the different Ka values for things. And acetate, this is kind of the one I drew here. You see the hydrogen that it's going to lose is in red, and it tells us the Ka value there, 1.8 times 10 to the negative 5. And since that's negative 5, you could probably get away, instead of using the quadratic, with doing an approximation of that, because I think it would be pretty small. But the quadratic formula will always work for you, always give you that right answer. Again, in this situation, we have the pH is equal to the pKa value. So to find that in this case, I can even pull up a calculator. I can just say the negative log, and then I'm just going to put in the value for the Ka value. So 1.8, do a little e for the times 10 to the negative 5. And there's 4.74 is going to be the pH at that half equivalence. It's a quick and easy thing to calculate once you know the Ka value for it. And I'm just about out of time, so I'm just going to mention at this point here, we've surpassed the number of moles of our original weak acid. We've surpassed it by, if our initial was 25 milliliters, again, this only works because of the same concentration. Otherwise, what you'd want to do is take that 0.100 molar, which is moles per liter, We want to multiply that by 0.025 liters. This is just 25 milliliters converted to liters, and this will equal the number of moles of your acid originally. So you should always be working off those moles of acid unless they give you something easy where the concentrations are the same for both of those. But at this point, we've surpassed the number of moles of acid that we had initially. So any mole of hydroxide we've added after that, we can calculate just using the idea of, we can assume that excess is equal to the concentration of hydroxide. The excess mole of OH, then divided by the total volume. So we don't do the Henderson-Hasselbalch after the equivalence point, because here it's after that equivalence point, right? So after the equivalence point, we no longer have a buffer. There's no acid left in there, because we're just eradicating it with this strong base that we keep adding in there. So we take the excess moles of the hydroxide atoms, and we had to divide it by that total volume. And that total volume is going to be the volume of the sodium hydroxide we added plus the initial volume of that weak acid. So in this case, it would be, 62.5? And the excess moles you could just find by taking the molarity of our base, and we multiply it by the that excess volume that we've added, that extra 12.5 milliliters. Thank you all again. Went a few minutes over. Best of luck. If you have any questions, definitely chime in with one of our tutors, and we'll help you out as best we can. Enjoy your weekend. Thank you.